The second major example for Ampere's law is what's called the toroid or toroidal coil. It's called that because it's wrapped around a torus or donut-shaped object. If you don't like the picture that I've drawn here, I've got some other ones. This is a picture of a toroid from the web. And this is an example from hyperphysics. I'm going to add another drawing for reasons that'll be obvious in a few minutes. I'm going to try to draw just a cross section What I invite you to imagine is that I've sliced the donut lengthwise along this direction so that we're only seeing the bottom half of it. Similarly, all of the wires have been cut. So what I'm hoping you can see by this is that the wires that are coming from the outside of the coil, they are carrying current out of the page, and the wires that are on the inner part of the toroid, they are carrying current into the page. I'm also going to label three regions on the original drawing. One is the outside, one is within the toroid, and the other part is, for lack of a better term, the donut hole. And we're going to solve for the magnetic field in each one of these three regions. The donut hole is probably the easiest because it's easy to see that any sort of Amperian loop that you would draw in this region would not enclose any currents. As you can see, this Amperian loop that circles around the inside of the donut hole doesn't enclose any currents, therefore we get no enclosed current. If that's the case, then that means this integral over here must be zero. And since the ds path is going to be some finite number, 2 pi r for whatever that r value is, then that means that the field must be zero. Similarly, outside of the toroid, in this region here, you can see that because of the way the wire is wrapped around the torus, every time you get a current that points into the page, that same wire carries current out of the page here. This means that if we were to start drawing an Amperian circular loop around the outside, this loop, although it encloses many turns of wire and therefore many currents, encloses just as many into the pages as it does out of the pages. And you can extend that argument to say that it carries just as many towards the inside of the rings as it does towards the outside of the rings. So this means that there is overall no enclosed current. And that gives us the solution for the region outside and the donut hole together. As for the region within the toroid, we are going to have to make an arbitrary decision about how many coils there are here. We can't do something like we did for a solenoid where there's just simply a number per unit length, and that's a number that you could vary. Think back to the Slinky lab where you were crunching the coils together or stretching them apart. Step one, as always, is to simply write down Ampere's law so you can remind yourself what its framework is. The next step, of course, is to think about the symmetry. As you can see from this cross-sectional diagram, there's clearly, once again, some circular symmetry going on. So it makes the most sense to choose as our Amperian loop some path inside here that simply goes in a circle around the ring. It shouldn't take you too long to realize that everywhere along that particular ds that we've chosen here within the ring has the same strength magnetic field. After all, each one of those points is equidistant from the current out of the page and the current into the page. And if they're tightly wound and fairly close together and so on, we don't even have to consider the fact that there's places where the field weakens. We can just make an assumption that the number of turns is sufficient that we can assume a constant magnetic field strength inside that within region. The second reason that choosing this Amperian loop makes sense requires you to do a little bit of imagination with the right-hand rule as it pertains to wires. If you think back to that right-hand rule, you have wires that have circular magnetic field lines surrounding them. So with these currents that on the top of the toroid are carrying current in this direction, then you have to sort of envision that the magnetic field loops sort of do this. That they loop around. I know I didn't draw that very well. The idea is that you have these concentric circular loops that surround the wire. They are in this direction above the wire. They are in that direction underneath the wire. So the result is that you get a magnetic field that points that way, at least for the within part of this problem. All this is simply to point out that the magnetic field inside that toroid is already going in circular lines around the inner region of the toroid. So this is a perfect example to see how the symmetry of our loop matches exactly the symmetry of the magnetic field. An alternative way to try to visualize this is to imagine each one of these things represents a wire carrying current. If the current is out of the page, then you have magnetic field lines that are in counterclockwise directions for this section, and you have magnetic field lines that are clockwise for the intersections. And the counterclockwise lines here point that way. The clockwise lines here point that way. So all of these magnetic field vectors add up to just a magnetic field that goes in a big circle around that ring. So as before, this thing that starts out as a pretty intimidating type of integral that calculates magnetic circulation simply becomes undot producted. And since the magnetic field has uniform strength, once again we can take the magnetic field out of the expression. And all that remains is to choose some arbitrary radius for our Amperian loop. So this takes care of the left side of the expression. As for the right side of the expression, we simply have to count up how many wires are there that are being enclosed by this dashed circular line. And well, you can count with me. 1, 2, 3, 4, 5, 6, 7. There's n of them. And really, that's it. The toroid is often given as an example of a good place to have a very strong yet highly localized magnetic field, because the magnetic field in the region outside drops off very rapidly to zero for this kind of reason. The magnetic field inside here is zero for similar kind of reasons. So it's a highly localized and very strong magnetic field. The second, of course, is the solenoid.